Ross, I'm going to mute myself not to interrupt you.
Sure.
Sure.
And I shall share my screen.
Of course, we're awaiting that.
Okay. First of all, I would like to thank IGSMP for creating this webinar. And I'd also like to extend a special thank you to Selena Leo for managing the effort and for kindly inviting me to make a presentation. My name is Frederick Narcross, and I'd like to welcome you to this presentation entitled Artificial Nervous Systems, a Breakthrough Technology for Cognitive and Neurorobotics. My goal today is to provide new information about neuro and cognitive robotics and show how that information integrates with artificial nervous systems to provide a breakthrough architecture to advance these fields. First, about cognitive robotics. Cognitive robots are a natural evolution of the concept of embodied cognition. And embodied cognition, in turn, is the theory that many aspects of cognition are directly influenced by an organism's entire body, including sensory and motor systems. The learning which occurs with embodied cognition happens because of the rules the system acquires in being exposed to the environment. Learning is attributed to having both passive and active states. Passive learning occurs by simply being exposed to information, and that information is organized as the syntax of a grammar. Active learning occurs by utilizing that which is passively acquired, learning by doing and practicing. The information so acquired by this active effort is organized as the semantics of a grammar. And this is how babies learn language, and how musicians learn music, and how athletes learn to play a sport. Grammar can be understood as the organizing principle that promotes both passive and active learning. Grammar consists of the rules for construction of the language, which is syntax, and grammar consists of the rules for interpreting the truth and the meaning of the language, which is semantics. Grammar also has a broad and general meaning. It circumscribes how to learn a subject. It circumscribes how to make use of that which is learned so that it can be utilized and practiced. And grammars are present in the learning of the arts, sciences, sports, and natural language. Because the brain is so adept at learning or acquiring grammar, it strongly implies that this is no accident. One could conclude that the brain is, in fact, wired to learn. Further, the wiring would have to be present across the brain regions that govern vision, hearing, the body's position in space, which is kinesthesia, and finally, the planning, preparing, and execution of motor control. Virtually the entire cerebral cortex must have this wiring. A candidate for the wiring, which is present across the entire cerebrum, is cortical columns. And despite their variations, they are a universal microfunctional structure. Columns are multi-layered collections of neurons, which permit three-dimensional neural information relationships and flow. And unlike machine learning and deep learning, columns don't use algorithms and require no maintenance and tuning. Columns can enhance or restrict information movement and can form relationships with neighboring columns for feature extraction in primary sensory cortex, And here, a column representing the permutation of the inputs establishes a vertex for the particular feature input. The vertices are joined together into increasingly larger collections of features. For example, all the lines in a face. And then the entirety of these collections are brought back together into a point. And that point is again like the vertex of a triangle, which ultimately represents a permutation of all of the data and all of the permutations residing behind and connected to it. Also, beginning at the base of the triangle, all of the features are forward connected to their next higher collection, such that the next time the same data is presented, it will follow the connected paths to elicit activation of the vertex. And once the vertex is established, feedback presented to the vertex will travel back through the levels collected below it that are still warm from previous activity. This will enable the vertex activation to retrace the connections in a backwards fashion, all the way back to the data presented to the base of the triangle when the entire forward activation began. In the future, feedback activation of the vertex will elicit the data at the triangle's base. The entirety of this feed forward and feedback procedure is similar in principle to that of deep learning, except that deep learning requires hundreds to thousands of iterations, and the human brain can accomplish this in one shot. The fact that cortical columns can accomplish this feat is because columns have significantly more functionality and flexibility than deep learning nodes, which represent a primitive and very non-biological neuron representation. The previously described functions, which columns perform, take place within the primary sensory cortices. In single modal association cortices, which are the association cortex connected to a single sensory cortex, the columns began to integrate connections between the vertices fed forward from the primary cortices. These high-level connections can be considered next in kind and enable, for example, the recognition that a yellow ball and a red ball are both balls. In multimodal association cortices, which are the association cortex connected to multiple single modal association cortices, the columns begin to integrate connections between the single modal association cortices. And these new connections are connected across time boundaries. These high-level time-dependent connections can be considered next in time and support such things as learning the lyrics to a song or remembering the successive events in a video. Cortical columns can be biologically modeled and massively replicated using artificial nervous systems. And now a few words about neurorobotics. Although columns can automatically acquire syntax, they cannot automatically acquire semantics. That is why ChatGPT and other machine learning and deep learning algorithms will not be capable of artificial general intelligence. They have no deep understanding of themselves or the world that exists. And despite ChatGPT's tremendous ability to acquire syntax, as far as deep understanding of the meaning of words, ideas, and reasoning, they are helpless. However, embodiment does support the acquisition of semantics. And because robots support embodiment, robots should be capable of acquiring the semantics of grammar. And this assumes that the robots have cortical columns to support the acquisition of syntax and semantics. The same columnar architecture, which supports the passive acquisition of syntax, also supports the active acquisition of semantics. And again, artificial nervous systems support the modeling and construction of cortical columns. In other words, robots with artificial nervous systems can create general purpose learning machines. Now, a few words about artificial nervous systems. Robots and artificial nervous systems are symbiotic. Artificial nervous systems provide robots with high integration and no algorithms. And robots provide artificial nervous systems with embodiment for grammar acquisition suitable to create general purpose learning machines. An artificial nervous system is perfectly positioned to provide the technology to grow the fields of cognitive and neurorobotics beyond their current state and into the next generation of robots. This next generation could learn virtually any subject, and with that learning secured, robots should be able to reason and act with intention and predict the results of their behavior. This implies that artificial nervous systems would be a breakthrough in the field of robotics. They would have the ability to learn any subject. They would have the ability to practice and improve their performance. And they would be able to predict the results of their behavior. There are reasonable expectations that they would become self-aware. The tools for construction of artificial nervous systems do exist in a minimal viable product form. The artificial nervous systems which result from the tool's construction can operate on regular computing hardware and FPGA microchips for massive parallelism. And this level of parallelism cannot be achieved even with massive number of GPUs. The tools are very comprehensive in their ability to biologically model nervous systems, and the features list is pages in length. The features are suitable for modeling virtually any neurophysiological or neuroanatomical construct. Utilizing the tools requires a pre-build process where the neurons, astrocytes, columns, etc., are identified or customized. Axon communication paths are defined both locally and for longer ranges. And additionally, the distribution of column types and their quantities are established. That process is then followed by an automated build process for the central nervous system, which is followed by an automated build phase for the peripheral nervous system, which is followed by an automated intracolumnar and intercolumnar connection phase. And then finally, a run, monitor, and control of the system in real-time, near real-time, or simulation mode. The tools provide everything needed for a software and control system that create cognitive robots with a neural basis. The tools can be used to develop robots with capabilities that begin where machine learning and deep learning end. The tools should enable biologically modeled intelligence, or BMI, that artificial intelligence, AI, is incapable of modeling. And finally, I would like to leave you some takeaways. The brain is pre-wired to acquire grammars. Cortical columns are an architecture that supports the acquisition of grammars. And cortical columns support one-shot feature extraction and the creation of next-in-kind and next-in-time relationships. Cortical columns can be massively instantiated using artificial nervous systems. Therefore, artificial nervous systems are symbiotic with robots and represent a breakthrough technology for cognitive and neurorobotics. Thank you. I sincerely appreciate your time and consideration. Are there any questions?
Sorry, sir, I got disconnected. That was very wonderful. Actually, you graced our webinar with your presence and your presentation. As someone who is doing neuroscience research, that was really interesting to me myself. I'm pretty sure everyone has used a lot. Actually, the part that you mentioned, the comparison between the columns and deep learning and machine learning was really interesting to me. And I will sure read the questions to you. Do you have my voice, sir?
Yes, yeah,
Okay, sure.
perfectly well.
Okay, that's great. How long before the artificial nervous system can mimic, say, 80% of the actual real nervous system abilities?
Well, that depends a lot on,
Uh,
I'm sorry.
yeah, that's it. I was just seeing if the rest of the question is somewhere.
Okay, okay. The answer to that question, it depends on time, money, and people. I would like to make this technology available to the general public in open source form. And a good way to go about doing that would be to create an open foundation supporting such an effort, and with enough people and enough resources, it shouldn't take decades to accomplish that 80%. And actually, that 80%, it's an interesting kind of a question, because the vast majority of the cerebral cortex is oriented towards motor function. And because a robot, for example, has orders of magnitude less functionality than a human, there's a radical reduction of, let's say, cortical support that is necessary to power a robot with the same level of intelligence. So it might not be necessary for 80% of the cerebral cortex to be reproduced in order to create interesting and useful robots. I hope that answers the question.
Thank you, sir. Thank you, sir. I really thank you. And let me see. There was another question. What is neuromorphic computing? That's another interesting question, and I highly appreciate if you can answer that.
Sure, no problem. Neuromorphic computing is based on a hardware configuration to emulate neurons at the microchip level. It has multiple different approaches for achieving that. A classic one is called memristors, where materials are put together that replicate kind of a memory component, and then massive numbers of those are put together. That's one approach. The approach that I've used with some success is again using FPGA microchips, because there you can create a neuron, and it operates as its own independent entity. It doesn't need external memory. It doesn't need floating point hardware. It doesn't need anything else. It just resides on its own in the middle of this FPGA, along with thousands to millions of other neurons, all operating independently. And so consequently, this is massive parallelism on neuromorphic hardware.
Thank you so much, sir. I really appreciate your answers and your time. Thank you for your presence. And I
really appreciate your presentation. I really use that myself, I can say, as a neuroscience researcher. Hope to use your knowledge for sure in the future.
Thank you very much for the kind invitation.